So in our Honors Math 2 Unit 7C review, the first problem says, how do you find the period of a sine function in the form of sine, y equals sine of b of x? So our rule for period is that it's 2 pi over b. So we're going to plug in the value we get for b into this equation. Then we get 2 pi over b. We simplify that, and that gives us what the value of the period is. So this is a key equation we have to remember to get from the b value, the coefficient of x, to the period. Number 2, describe the effect of m on the graph of y equals m sine x. M is the amplitude. And so if we look at the graph of sine, the amplitude is really the height of the function. It's that vertical stretch of how much it goes up. And so if the a was, or m, m there, m was 1 unit, it would be up 1. If it was up 5 units, it'd be a 5. So we always had that value. It also, if m is negative, is a flip. It reflects across the x-axis. And what I mean there is if I drew out sine function where it was, let's say it's negative, it would go down first and follow that function. So it'd be a reflection down. Number 3, what is the maximum value of the function 7 sine x over 3? Well, I know since I have a 7 there that the function's going to have a max up here at 7. So maybe we should find the point. So if our period, we're going to say 2 pi over b equals the period. So 2 pi over 1/3 becomes 2 pi divided by 1/3, which is 2 pi times 3, which is 6 pi. Right here. Half of that is 3 pi. Half of that is 3 pi over 2. So the maximum here is the coordinate 3 pi over 2, 7. For number 4, what is the length of one period of the function of negative cosine 2x? The 2x is what we're focused on because the period is equal to 2 pi over b. So we go 2 pi over 2 because b is 2. We get that pi, so the period is pi. Number 5, what is the length of one period of the function of 5 cosecant 3x? So our period is equal to 2 pi over b. b here is 3, so that's 2 pi over 3. So we'd say that our period is equal to 2 pi over 3. What is the length of one period of the function of secant of pi over 5x? So we'll go period equals 2 pi over b. b is pi over 5. So that's 2 pi divided by pi over 5, which becomes 2 pi times 5 over pi. The pi's reduce out, divide out, we get 2 times 5, and our answer is 10. So our period is 10 units. It is not 10 pi, it is just 10 units. Number 7, where does the maximum occur in the first period of our function negative 2 cosine 2x? Now we already found earlier that the length of that period was pi. So we'll still show it though. The period is 2 pi over b. b is 2, so it's pi. So that means cosine with a negative starts here and at the minimum. So that's what one period will look like. It ends at pi. Half of that is pi over 2. Half of that is pi over 4. And then we have 3 pi over 4. So those are our 4 steps going through looking at this function. So now negative 2 cosine of x, we're looking for the maximum. That's going to be at the peak. So the amplitude there is 1, or the height is 1. And it's going to be at pi over 2, positive 1. Now, if it was a positive cosine 2x, it would have been up here. It would have been flipped back, and we would have had at 1 and pi a maximum. But since it's flipped, it's down. It's up here. Okay, number 8, where does the minimum occur in the first period of the function 5 sine 3x? So our period is 2 pi over 3. And we're looking at sine. Sine starts at 0, finishes the period there. That is at 2 pi over 3. The minimum I see is at this 3/4 mark. So it's the third step. Amplitude is 5 and -5, so we need to figure out what this is. Now what I could do is go through and find half of 2 pi over 3, which puts me there. I could find half of that, but really if I know it's the 3/4 mark, I'm going to take 2 pi over 3 times 3/4 to figure out what this coordinate is. So this becomes 6 pi over 12, which is pi over 2, which is right there. So the minimum is at pi over 2, and the y value there is -5. Number 9, where does the 0 occur on the function cosine pi over 5? So my period is going to be 2 pi over b, which is 2 pi over 5, which we'd say is 2 pi divided by pi over 5, or 2 pi times 5 over pi. This comes out to be 10. So I'm going to go to cosine. I have, there's the cosine period. Keeps going if we needed to. We know it finishes one period at 10. Our 3 steps are the 0, minimum, and 0. So that's going to be 5. That's going to be 5 halves, or 2.5. And this is going to be 15 halves, or 7.5. So it looks like our zeros are at 5 over 2 and 15 over 2. Now if we went through and predicted where the next one was, if this was 2.5, 7.5, I see I added 5, 12.5 is actually our next one, which would be 25 over 2 as well, and we could keep listing them on. It likely just wants one period, so we would indicate those 2 points. Now if it wants it as a coordinate, we'd say 5 over 2, 0, 15 over 2, 0. Okay, number 10, what are the excluded values of 3 cosecant x? So in order to get to 3 cosecant x, we first have to look at its reciprocal. The reciprocal of cosecant is sine, so I'm going to first use 3 sine of x to work with. So 3 sine of x tells me I have an amplitude of 3. And then period is 2 pi. This would be pi, this would be 3 pi, and we have, whenever there's zeros, we have vertical asymptotes. So now, cosecant is what I'm drawing in blue. It's not the graph of sine, it's the graph that comes in with the vertical asymptotes and hits the minimum or maximum of sine. So, what are the excluded y values? Well, cosecant is not happening in here. It's always coming down, hitting that maximum or minimum, but nothing's happening here. So the y values, it doesn't work between -3 and +3. Okay, but does it include 3 and -3? Well, actually if it comes down and it hits this point, it does. So we're just going to use the less than, not the less than or equal to. So our excluded values are for -3 and +3, with y not including those values. Okay, well let's look at the same idea now with -2 secant x. So in order to do -2 secant x, we're going to do -2 cosine x. So cosine, -2 is going to start at its minimum. I'm going to draw my vertical asymptotes. And then we have the graph of secant. So if my amplitude was -2, +2, I kind of have this range inside here that nothing happens. So my excluded values are going to be between -2 and +2. Which again, we kind of see here that amplitude is actually really indicating. It's between that amplitude, the positive and negative of it, is where those excluded values do occur. Okay, number 12, find the amplitude and period of the following for y equals 3 over 2 cosine pi over 2x, or pi x over 2. I'm going to put that the amplitude is 3/2. The period is 2 pi over b, which is 2 pi over 2, which is 2 pi divided by pi over 2, which we get 2 pi times 2 over pi, and it comes out to be 4. So period is 4, amplitude is 3 over 2. For number 13, negative sine of 2x over 5, your amplitude, we're not going to say it's 1. The amplitude in this case is positive 1. That's not the negative, because I've been negative 1 there. It's a positive 1. That's still the distance from the kind of center axis up to the top. So that's 1. Period. We're going to do 2 pi divided by 2/5. So that's 2 pi divided by 2/5. Then we get 2 pi times 5 over 2, which comes out to be 5 pi for the period. Number 14, sketch 2 periods of 2 cosecant 2x. So before I do that, I'm going to graph 2 sine of 2x, which is going to have a period of 2 pi over 2, or pi. And I know sine starts at 0. There are periods. So if this is pi, this is 2 pi. That's my second period. Half of pi is pi over 2. Then I have pi over 4, 3 pi over 4. Halfway between these two is going to be 3 pi over 2. This would be 5 pi over 4 and 7 pi over 4, which are actually the 45-degree markings that we had whenever we did the unit circle, so maybe those fractions start to look a little bit familiar. We have a 2 and a negative 2 here. So anywhere we have a 0, we're going to draw in a vertical asymptote. And then our graph would look like this. And this is cosecant in blue. Okay, next we have secant of, or negative secant of 2 pi x. So we're first going to look at negative cosine of 2 pi x. The period there is going to be 2 pi divided by 2 pi, which is 1. So we have cosine, and it's negative, so it starts at the minimum. And this ends at 2 because our period is 1. So then we have 1/2, 1/4, 3/4. This would be 3/2, 5/4, and 7/4, which are actually the same fractions as the previous problem, but in this case there's no pi on it. So here's our cosine. We got a -1, +1 there. Let's draw in the asymptotes. We have graph going down, going up, facing down, facing up, facing down. Okay, next let's go to number 16. We have -3 sine of 4x over 3. Let's start with the period. We do have a restriction there, but I want to know the period first. So I have 2 pi over 4/3 is 2 pi divided by 4/3, or 2 pi times 3/4. Gives me 3 pi over 2 as the period. I actually want to go both directions. So 3 pi over 2, if I go in both directions, is a full period. So I want to go from -3 pi over 2 to +3 pi over 2. I'm going to do a period in both directions. 3 and -3 are the values I'm going to use. This one's going to be a little condensed because I kind of ran out of room, but negative sign starts going down. So let's break into our 4 steps. Sine going down is going to go down, hit the minimum, through 0, up, hit the maximum, back to 0. Negative direction, it's going to the maximum first, down to 0, minimum, back to 0. And so there's our graph, which from -3 pi over 2 to +3 pi over 2. Okay, now for 17, cosine of 2 pi over x, or 2 pi x, and then we have a 3/2 in front. I'm going to do 2 pi divided by 2 pi. Gives me a period of 1. I'm going from -1 to +2. And if my period is 1, each of these parts represents a period. And since 3/2 is my amplitude, let's go and break these up into fourths. So cosine, we're going to start up here at the maximum. We go through 0 to minimum, through 0 to maximum, 0 to minimum, 0 to maximum. Other direction, 0 to minimum, 0 to maximum. And there's our graph from -1 to +2 of 3/2 cosine 2 pi over x. So number 18, we need to write the equation for what we already have, but it's not really based on its first period. Let's just say based on the interval. So what do we know? We know it starts at 0 and goes up. So it's not starting at maximum or minimum. So I'm kind of thinking it's going to be sine. 7 is where it peaks in -7. So I'm thinking A is 7. I don't know if it's positive or negative yet. We'll get there. -3 looks like the end of a period. So if the period is equal to 3, I could go 3 equals 2 pi over b, 3b equals 2 pi, or b equals 2 pi over 3 by kind of manipulating things around. So really the last thing I need to know here is it a positive or negative? Now if I continued this graph on, it would go down, so from 0, so that kind of makes me think it's going to be a -7. So putting this all together, I get -7 sine of 2 pi over 3x. And that's not even looking at the interval that I have. Okay, well, let's look at 19 now. On 19, what do I notice first? I got the 4 and -4. So amplitude looks like 4. Could be plus or minus. Let's wait on that. It starts at a maximum. So I'm going to make that a cosine. So really we need to know the period. Now if it started here and ended here, I need to know what that point is. Well, so far I have pi over 4 and 3 pi over 4, which are actually between two zeros. But I have this middle step here. Halfway between 1/4 and 3/4 is 2/4, or pi over 2. So if that's pi over 2, and that's half of the period, the full period would end at pi. So now I can say pi is equal to 2 pi over b. We get b pi equals 2 pi, or b equals 2. Now I can kind of see my equation is going to be y equals 4 cosine of 2x. I'm going to take the positive because it starts at the maximum, and this is my equation. For number 20, find the sine curve with an amplitude of 4 and a period of 2 pi. So we first need to say the period is 2 pi. We go 2 pi equals 2 pi over b. b times 2 pi equals 2 pi by multiplying over, and we get that b is just 1. So my equation is going to be y equals, we have a sine of x, amplitude is 4, goes out in front, that's going to be 4 sine x. A cosine curve with an amplitude of 1, a period of 4, and a y-intercept of -1. So that means it actually has to hit down here at -1. So if that was my cosine curve, I would know that a is -1. b, we got to solve, because we know the period is 4. We'd say 2 pi over b. 4b equals 2 pi. b equals 2 pi over 4, which is pi over 2. So I put it all together, it's going to be a negative cosine of pi over 2x. For number 22, we have a cosecant curve, amplitude of 3, period of pi over 2. So let's say pi over 2 equals 2 pi over b. This becomes b times pi over 2 equals 2 pi. b times pi equals 4 pi, so b equals 4. So this one we're going to go, the amplitude is 3, x, because b is 4, and we have our equation. For number 23, a sine curve that has a maximum at 3 pi over 4, 2, and a minimum at pi over 4, 2. Let's get some points marked here. So sine curve may look like this. So if it has a maximum at 3 pi over 4 and a minimum at pi over 4, well, that's a problem because that's saying the maximum happens later on. So what that actually means is we need to flip it. So let's do this. It has to go down first, then up. So this is pi over 4, negative 2. This is 3 pi over 4, positive 2. So I already know with the negative 2, positive 2, it starts out as y equals negative 2 sine. We need to adjust for the period. So if this is pi over 4, this is 3 pi over 4, halfway between these is pi over 2. That's half a period. So my full period is pi. So I'd say pi equals 2 pi over b. This is giving me b pi equals 2 pi, so b is 2. So we're going to go 2x. So our equation is y equals negative 2 sine 2x. Okay, now a cosine curve with zeros at pi over 4, 3 pi over 2, and a minimum at pi over 2, negative 2. Let's just draw a cosine curve to start. Now anything we need here, looks like it's going to be a positive. If not, we'll start over. So I have a 0 here at pi over 4. I have another 0 at 3 pi over 2, and a minimum at pi over 2. Let's put this here. Okay, well, if this is pi over 4 and this is pi over 2, then this is 3 pi over 4. Maxes out at pi. So do we hit another 0 at 3 pi over 2? It doesn't look like we actually do. We're going to call this a typo, and let's just make this 3 pi over 4 as our other 0. Otherwise, it's a shift that we really don't know how to do. So I have pi over 4, 3 pi over 4 are zeros. Make sure you make that 3 pi over 4. So now we need to graph the equation. We had a positive 2, negative 2. So that's going to be a 2 cosine x. Our period is pi. Like we saw up above, when it's pi equals 2 pi over b, you get that b is 2. So y equals 2 cosine 2x. Number 25, a secant curve with asymptotes at pi over 8 and 3 pi over 8, and a y-intercept at 4. So graph secant, I'm first going to graph cosine. So this here, we have asymptotes at pi over 8, 3 pi over 8, okay, and an intercept at 4. So I know in my secant it's going to be 4 secant something x. I need to figure out what that something is, what makes the period. So let's figure out where this period occurs. So if this is pi over 8 and this is 3 pi over 8, halfway between that is 2 pi over 8, which is pi over 4. Now that is actually half the length of the period, so the period will end at 2 pi over 4, or pi over 2. So now pi over 2 equals 2 pi over b, because that's the period and we need to solve for b. We get b times pi over 2 equals 2 pi. This is b times pi equals 4 pi, if I multiply the 2 over, and I get that b is now 4. If b is 4, it goes here, and we'd say that y equals 4 secant 4x. So now we shift gears and start looking at the trig identities. I would have your rules out as you go through these. These are not necessarily the fastest way to get to these. It varies. There's multiple ways to solve them, so if you don't entirely agree with my method, but yours follows the proper steps, that is okay. So first off, a little basic one, secant x, cosine x. I want to write secant as its reciprocal, which is cosine x. So I get cosine x times cosine, or times 1 over cosine x, which becomes cosine x over cosine x, or we just get 1. 27, I have cosine theta over cotangent theta. I'm going to split these up and make this cosine theta times 1 over cotangent theta. This is going to be cosine theta times tangent theta, which is then cosine theta times sine theta over cosine theta. These will reduce out the cosines, and so I'm left with sine theta. Cosine squared theta minus 1 looks a lot like a Pythagorean identity. We have sine squared theta plus cosine squared theta equals 1. So if I kind of got the cosine and the 1 with same side, it looks like 1 minus cosine squared theta equals sine squared theta. But that's not entirely what I want. I need these to switch signs. So if I wanted to switch signs, I could just multiply everything by -1. And this would become -1 plus cosine squared theta, or cosine squared theta minus 1. So I'm going to replace cosine squared theta minus 1 with a negative sine squared theta. Number 29, I have 2 minus 2 sine squared theta on top, and I have a tangent squared theta on the bottom. First thing I'm going to do, I'm going to factor out a 2 on top. That leaves me 1 minus sine squared theta. And you know that tangent squared theta looks like a Pythagorean identity, and 1 plus tangent squared theta is secant squared theta. So let's get that taken care of. Now, this 1 minus sine squared theta is cosine, so this is now 2 cosine squared theta over secant squared theta, which we could then rewrite as 2 cosine squared theta times 1 over secant squared theta. Secant is the reciprocal of cosine, so this is actually now cosine squared theta. So now we have 2 cosine squared theta times cosine squared theta, which is 2 cosine to the 4th theta. Okay, number 30, I have cotangent squared theta plus 1. That is the Pythagorean identity for cosecant. So now 3 over cosecant squared theta, we could write as 3 times 1 over cosecant squared theta. Cosecant is the reciprocal of sine, so that becomes 3 sine squared theta. Number 31, actually these two are kind of jammed together. We're going to multiply them to distribute in. I get cosine. Now, you know, before I do that, let's look here. Secant squared theta, we could use the Pythagorean identity for that. But you know what, I'm going to go with distribute. So I'm going to go cosine squared x minus cosine squared x secant squared x. Cosine squared x minus cosine squared x times 1 over cosine squared x, because secant is the reciprocal, basically turns this whole thing into 1, cosine squared x minus 1, which should look familiar because we had this earlier, that cosine squared theta minus 1 is negative sine squared theta, so then we can turn that into negative sine squared theta. Now right next to it is 32. 32, we're going to use the difference, or think of binomials. Cosine k plus sine k squared is going to give you a cosine squared k plus 2 cosine k sine k plus sine squared k. And that's like saying a plus b squared gives you a squared plus 2ab plus b squared. What's important here is I have cosine squared k plus sine squared k. I'm going to put those two together because these become 1, so I'm left with 1 plus 2 cosine k sine k. Number 33, I'm going to think factoring because I both have a sine x in both of these. I'm going to take that out of both. 1 minus cosine squared x is left inside. That is an important one because that is the Pythagorean identity for sine squared x. So then we get sine, we have 3 of them, so we say sine cubed x for 33. Okay, 34, 1 minus sine squared x, again with our sine squared theta plus cosine squared theta equals 1. If you subtract over the sine squared theta, you get cosine squared theta equals 1 minus sine squared theta. We can just substitute, and our answer is cosine squared theta. 35, we're going to multiply. This is actually a difference of two squares, and becomes cosecant weird symbol squared minus 1, which can go to a Pythagorean identity of 1 plus cotangent squared theta equals cosecant squared theta. Well, I want to get this to be the same, so if I subtract 1 from both sides, I have the same thing, so we're going to say that it is cotangent squared theta, and that's not a fraction, that's the actual answer. Number 36, I'm going to factor out the 4's and get cosine squared theta plus sine squared theta. On the inside, this becomes a 1, so it's 4 times 1. The answer is then 4. For 37, I can factor a cosine out of both, and this leaves me with sine squared theta plus cosine squared theta, which looks pretty familiar because this turns out to be 1 times cosine theta, which is just cosine theta. For number 38, I have the stuff on top, really on the bottom, that 1 minus cosine squared theta is going to become sine squared theta. Bring down the numerator that I have. I have a sine on top, 2 on the bottom, so this is going to become cosine theta over just a single sine theta by dividing out the sine from both. This I can go a little bit further because cosine over sine is cotangent, so our answer will be cotangent theta. For number 39, do not take the square root of secant theta minus 1 and tell me it's, or secant squared theta minus 1 and tell me it's secant theta minus 1. You cannot take a square root when you have addition or subtraction. What we're first going to do is use the Pythagorean identities. Secant squared theta minus 1 is tangent squared theta, and cosecant squared theta minus 1 is cotangent squared theta. Now when I take the square root of those, I get tangent theta over cotangent theta, which is the same as tangent theta times 1 over cotangent theta, or tangent theta times tangent theta, which is tangent squared theta. Number 40, we're going to do multiplying like binomials. We're going to get 1 plus 2 tangent theta plus tangent squared theta plus 1 minus 2 tangent theta plus tangent squared theta. These two terms become 0, so I'm left with 1 and 1 and 2 tangent squared thetas, which have a common denominator of 2, or common factor of 2. So I'm left with 2 taken out. 1 plus tangent squared theta. 1 plus tangent squared theta is secant squared theta, so we say 2 secant squared theta. For number 41, I'm going to break these into 2 fractions. You cannot cross out the tangent squared, so don't you dare do that. But what I can do is make this 1 over tangent squared theta plus tangent squared theta over tangent squared theta. Now 1 over tangent squared theta is cotangent. Tangent squared over tangent squared is 1. But if I had something of cotangent theta, squared theta plus 1, another Pythagorean identity, and that comes out to be cosecant squared theta. So then we get to our proofs. Now the nice thing about the proofs is they're just like the simplifying we just had, but we know the end result. So your goal in the proof is not to show me the answer that you get, it's to show me the steps to how you arrive to that answer. Show all your steps. So for something like 46, I'm going to take the more complicated side first. Cotangent theta is 1 over tangent theta times tangent squared theta. I'm going to put that together and get tangent squared theta over tangent theta. This reduces tangent squared over tangent just to be 1. Tangent theta, it comes down, we get tangent theta equals tangent theta. For number 47, I'm going to pick the right-hand side and work with that. I'm going to factor out a sine from both terms. I'm left with sine squared theta plus cosine squared theta. Now, sine squared plus cosine squared is 1. It's Pythagorean identity. So what I'm left with now is sine theta, which is the same. That's sine theta. For number 48, I'm going to split this into two fractions. On the right-hand side, I have 1 over secant squared t minus secant squared t over secant squared t. Reciprocal of secant is cosine squared t, and then I have a minus 1. Now this we've seen is close to our Pythagorean identity. This is actually a negative of 1 minus cosine squared t. That we know is sine, so it becomes negative sine squared t. Factored out a negative to get it to the form we liked. For number 49, I'm going to split the fraction on the right-hand side. So I'm going to make this 1 over sine x minus cosine x over sine x. Reciprocal of sine is cosecant. Cosine over sine is cotangent. And now it matches, cosecant x minus cotangent x. For number 50, I could start with 1 and turn it into this, but that would be terrible. So instead, let's work with the right-hand side. I'm thinking I can multiply, kind of distribute in to this and multiply sine cosine times tangent and multiply it times cotangent. So I get sine theta cosine theta tangent theta plus sine theta cosine theta cotangent theta. So I got sine theta cosine theta, tangent is sine over cosine, and then sine cosine, cotangent is cosine over sine. Over here I have a cosine and a cosine. Those are going to reduce and I get sine squared theta. Over here I have a sine and a sine, gives me cosine squared theta. Together, sine squared plus cosine squared is our Pythagorean identity. It becomes 1, and we get the answer of 1 equals 1. 51. The way I approach 51 is I'm going to write them all out on the left-hand side as secant x times cosecant x times 1 over cotangent x. Now I'm going to change them all to be in terms of sine and cosine. Secant is 1 over cosine x. I have cosine x. And then cotangent is, that should be a cosecant. Reciprocal of cosecant is sine. Cotangent is tangent x, which is going to become sine x over cosine x. So now they have them all together. The sines are gone, so it's now, come over here, 1 over cosine squared x, which its reciprocal is secant. Secant squared x equals secant squared x. Okay, 52, I have tangent squared b plus sine squared b plus cosine squared b. These two stick out because that is our Pythagorean identity to just be a 1. Now I have tangent squared b plus 1, which is one of our Pythagorean identities, to be secant squared b equals secant squared b. Number 53, I have 1 plus sine squared k and 2 minus cosine squared k. Let's do this. Let's rewrite this. If this was 1 minus cosine squared k, I could work with it. It's not, though. But what I could do with the 2 is to split that. So now I have 1 plus sine squared k on the right-hand side, which matches. Okay, that one, there's probably multiple ways you can get to it. See if you can get one that's a little bit different than my method. All right, last page. Let's go 1 plus tangent theta squared and secant squared theta plus 2 tangent squared theta. I'm going to square the right-hand side. So squaring a binomial, we get 1 plus 2 tangent theta plus tangent squared theta, which looks like I got this part. So I kind of figure out what to do with this to get to secant squared theta. Well, I'm going to put those two together. 1 plus tangent squared theta plus 2 tangent theta off to the side. This is a Pythagorean identity and is secant squared theta. So 2 plus, I'm sorry, I get secant squared theta plus 2 tangent theta, which is what I want. 2 secant squared theta plus 2 tangent squared, no squared. Try this again. Secant squared theta plus 2 tangent theta. Whew. All right, 2 more. 55, 1 plus tangent squared w is a Pythagorean identity. So this is going to become secant squared w times cosine squared w. Secant is 1 over cosine squared w. Put them together, I get cosine squared w over cosine squared w, which is going to be 1. 1 equals 1. We get our answer. Last one, I'm going to work with the right-hand side. On the right-hand side, I have 1 over cosine x minus sine x cosine x over cosine x. Now, cosine x is secant. This one, I'm going to divide out the cosine x's, and I'm left with sine x. So then I get secant x minus sine x for my answer.